Hello everybody, my name is Boris and we are talking about tensor core programming or how to do matrix multiplication with the help of tensor cores. In previous, let's say not theoretical but practical video, we explained how to multiply two matrices with the help of fragment of matrices and the size of the tiles which we are taking from the matrices is corresponding to size of the fragments which are used inside the tensor core for the mutual matrix multiplication. So we pick up literally whole matrix A and whole matrix B into the fragment A and fragment B, and we are multiplying them inside of tensor core, and then we have result which is fragment C, and then we take that fragment C and put it in into the result matrix C. But this is all fine and good because the size of the matrix corresponds to size of the fragment that we are using to multiply them inside of tensor core. So we want to explain what's happening here in this kernel more in details and more visually, because if we doing just this code without special, let's say, explanation, it's very hard to understand. So we want to have a closer visual look what is happening there. So we have some kernel core which will kernel function which we will call later in the main program with a specific with specific, let's say, argument inside of inside of a thread and the block fragment, which is one block with 32 threads. They say it's enough to do this inside tensor cores. What do we want to say with this? This is the case for size of the fragment A and fragment B corresponding to size of input matrices, and this is 16 times 16 in this case. And we have one block or warp is enough with the 32 threads is enough to do this multiplication inside of tensor core. Why is that? We will discuss later, but let's go to the practical part. So we picked up this kernel function and we will go one by one through these callings of the methods from the library which is inside the matrix multiply and add .h header, and we will see what is exactly happening in the architecture. So this is video about architecture. This is just video part of the video where we getting know what we are exactly doing. So we picked up this full kernel function to analyze it. So tensor core programming theory, we have, as we said in CUDA core programming, that we have different parts where we're moving data from, and to how to do the manipulation of the data or data and do the different parts of the operations on the data. So we have GPU RAM, which is, let's say, standard in the CUDA functions calling, like moving from the CPU RAM and so on. And then we can move that data in some specific manner and some specific methods from the GPU RAM, DRAM to the register file, which are the fastest memory in the backyard. So we putting data for manipulation inside the register files, so Tensor Core can approach this data. And I think the Tensor Core can only approach this data from the register file, but we will see later is there any other possibilities. So let's say if we going from the GPU RAM, we put some matrix C, A, matrix B, and matrix C, or reserved some space inside of it in the GPU DRAM. I forgot to write it down. Then we must put that part of the matrix inside of register file of fragments A and B. In this case, a matrix A corresponding to the fragment A in size 16 times 16. That's how we choose our example to be. Also similar for the fragment B, and the result matrix C will be the size of the fragment C, which is inside the register file. And register file is uh, fastest memory in a yard, so it can charge Tensor Core with data very quickly. We will pick up fragment A and fragment B and put them inside the Tensor Core for matrix multiplication, and then the result we storing in the fragment C, and then we putting fragment C to the GPU memory where is the reserve space for matrix C elements. So after operation is done on the Tensor Core, we put the results in fragment C, and then we moving from the fragment C to GPU DRAM for other kinds of manipulation of that data that we have. So we are returning back that C, and then if we want to show that data, we must put that data in the CPU RAM and represent that data in a regular way. So it's a long way of the data flow, but in this case, we are doing, we are seeing how data flows to be proceed, or some matrix multiplication is executed on them. So this is just the entry to see what kind of business, and to show a little bit of this data travel from beginning to the end, and what is entry. Entry is matrix A and matrix B, and what is return, it's a fragment C, or then matrix C. Operations for this example are done unlike the previous case on the Tensor Core, and in previous case we use mostly CUDA cores for execution. Um, we can go further. Yeah, this is in short that kernel function which is done on, of course, a kernel function, we forming threads out of it, but there's some specific parts and callings of some methods which are dealing with the register file, and this is mostly that part. Also this one, but there is also some specific instructions, like in this case, MMA, matrix multiply, and add and sync. This is Tensor Core operations, and these other operations are mostly dealing with the register files and moving the data inside and from, and or reserving space from it. So warp level fragments defining space. We defining space in a register file. I want to make sure that you know where are you manipulating this data, and where this data is stored. So obviously from here we are reserving some space or fragment for storing tiles of matrix A, and we call it fragment A. We see here that data will be write down row by row in this fragment by certain form and also by certain specific data, which is half. When we say half, it's a half of float, so it's a 16-bit floating point number. Also, we're reserving space from the for the fragment B, where will we store data from tile of matrix B, which is part of the matrix B, and put it here. And we making some space also in register file for the accumulator, where we will store the data from the different kind of operations. We defining the name of that space, or let's say maybe pointer. And in this case, results of matrix multiplication and multiplication of numbers of 16 times 16 will be 32 floating point, so standard data float, and that is also what you need to know, that difference. So it's not half, but result data are in form of float. Also, there's some instructions which are helping us to fill the fragment C to be neutral in sense of adding. So we defining also or putting the values into the fragment C. Also we load part of the matrices into fragments. And this is loading data from the RAM memory inside of frag A space, which is inside the register file, and also we are doing that for the part or tile of matrix B, and probably this is how many rows or columns we are using for that purpose, or maybe how many elements, but I think it's how many. Yeah, this define how many elements is inside how many elements is inside that column, and this is how many elements inside of that row, because it's signed as a K in literature. And then we have a method which is calling these matrices A and B, and neutral C is add on this multiplication, and we store everything on the fragment C, and this is standard form of the method which is executed on the tensor core. And the important thing to make a difference between, and that this is also very important for the future works, to make difference between thread, which is actually a copy of this kernel function, and the instruction for the tensor core. So this is much wider, but like in the case of CUDA course, only this part of this kernel function is executed in CUDA course, in tensor core. Like in previous case, just one instruction, a of I or C of I is equal to A of I plus B of I, or multiply, or whatever. That function, that instruction is only executed on CUDA core, because tensor core is only capable of doing this instruction. Also CUDA core is only capable to execute that simple instruction. But wider picture is a thread which is created out of tensor, which is created out of kernel functions, because threads are always defined or created from their multiplications of the kernel function. So it's very important once again to make the distinction between what is thread, which may have multiple instruction inside of it, and which is instruction for the specific part of the architecture like CUDA core, or in this case Tensor core operation. So after result is done and stored by this instruction in Tensor core in fragment C, we are storing that fragment C into the starting matrix C by certain order, which is provided here, which means row by row. So this is specific operation for the manipulation of data, which is moving data from the register file to the uh, DRAM or space which is reserved for the matrix C. Once again, to say also one very important thing, that size of the matrix A and size of the fragment A is the same also for the B and fragment B, also for the C and fragment C. But in later cases we will discuss when C is larger or much larger from the fragment, and how we actually um, doing stuff in that situations, and how we putting some tiles or some. But this one is one-on-one. So what did we just say? We want to explain these instructions one by one, and most of them are uh, referring to the register file, which is part of the memory closest to the CUDA cores and Tensor cores. That's where we store our, let's say, data if we want to be very quick in the execution. So these three functions from here for the matrix A, row by row, fragment A, and column by column for the fragment B, storing or reserving space, and this is how we directing what how we write our data, and this is for the reserving space. This is almost like some kind of pointer defined like this. And also for the C, we are put also type of the elements given space. These functions are actually let's say not functions but instructions. These instructions are reserving. It's like in DRAM or host RAM, we make the pointer, which is pointing, or similar to that, which is pointing to that register file memory. So these operations are concerning the register file as a memory location. So this is assigning space, like we assign some space in case of CUDA cores, in case of DRAM and CPU RAM. So to make some analogy, this is referring to the register file as a memory. Then we have filling the space for the matrix C to be neutral for the adding. Sorry, and there is a specific instruction from the set mma.h, which is filling that instruction, which is filling that fragment C with the zeros. So this is that instruction fill fragment. So this one is to create fragment or space for the fragment, and this one is to fill fragment, specific fragment, which we defined as accumulator, and also we give the name for that fragment C. I think we give the name. Maybe it's not obligatory to use the same name, but name must be recognizable, but we will check that. So we're filling that space which we defined previously with zeros, and then other instructions which are concerning the load of that register file space, which is reserved from fragment A and fragment B, with some elements from the tile of the matrix A. But in this case, tile and the size of the matrix A are the same, so no surprising in that. And also how many elements going row by row, I think this number represents. But we will explore that more later, because this one is representing the k, and k is representing the number of elements inside the row. Also, in this case, we have again same load matrix sync, same instruction, but for the fragment B and from the matrix B, also 16 elements in a column in this case, but defining of that space is defined here with this instruction. We use column major. So we putting in a register memory, we are putting the data column by column. We pick up column by column size of 16. We picked up some data, some elements, 16 of them, and from B, and we going column by column because we define it like that, and putting inside of frag B. And then we finally have instruction which is, let's say, ordering Tensor Core to do some operations and on elements of the fragment A and elements of the fragment B and elements from the fragment C by the defined instruction, and which is A times B plus C. And that's the only instruction that Tensor Core is doing and in charge of doing it. So this function is telling Tensor Core what to do, and Tensor Core reacts only on this instruction, and it's storing the result in starting fragment C. So nothing unusual here. We said that unlike the CPU, which have complex instructions and different parts of the architecture and the complex architecture, Tensor cores and the CUDA cores have simple architecture, which is doing only one task, and this task is it multiplies fragment A and fragment B, added to it fragment C, and then store everything to the fragment C. In this case, maybe there is some different way to do this instruction to change this, but let's not go further with that. But again, Tensor Core is doing that operation. In other words, oh sorry, I a little bit lost. Where am I? Ah, yeah. Yeah, we are explaining this. So this instruction is doing doing stuff on the Tensor Core. So no mysteries here, and how is doing what is picking up of as arguments is given in list here. After we store data in fragment C, we are again yeah, which is in a register file also, like all these babies and cuties little here. Then we are picking up what is stored in the register file as a memory and move it to the DRAM of the GPU in reserved space for the matrix C. Also 16 elements in row by row. That's how we move that data in logical order. So to repeat, only this one is hitting the tensor core, and these are mostly referring to the register file as a memory, as the fastest memory inside of this architecture. This one, this one, this one, and this one, and then we explain what they are doing. So let's go further to see it more visually, because more visual it's more clear, right? So reserving the space for tiles of matrix A, B, and C, and note in this case tiles are size of matrix. Okay, that's what we said on previously. What is doing this? We WMMA fragment. We creating space for fragment inside of the register file. For the matrix A, which will go row by row, and types of elements which are stored, which will be stored here, will be half. So, and also this comes as some kind of pointer for that memory location inside of the register file, and also specific sizes of this. Maybe we'll explain it a little bit later. Then also we are doing for the fragment B, but unlike the previous case where we going row by row and storing row by row and make it and putting data or putting data in memory in order to optimize the use for the matrix multiplication row by row, we are here doing column by column. We are storing in register file some data from the, but not yet. We are reserving space and defining how data will stored here in that reserved space when time comes to move that data, sorry. And fragment B is like some kind of pointer on that location. And also it will be filled with type of data half of FP, so it will be 16 bits. And then we creating or reserving space for the fragment C, and type of data will be 32 or float, and it will be accumulator, so it can receive data from different kind of operations which are we doing, and accept different kind of data which are we gaining from the operations done by Tensor Core. So it will be stored here as if we consider what we said previously. So all these operations is the reserved space inside of the register file, and we reserving that space in a specific manner, like row by row for the entry matrix, because we are picking its or because we are picking up its rows, and also for the fragment B, which is representing in this case matrix B, column by column, because that's how we're doing matrix multiplication, because we are picking up column by column from the entry matrix. And also we defining space for the accumulator where results will be stored after operations or instructions are done inside the tensor core. So this is defining. I hope it's clear. We make it more visual. What is happening with this register file and reserving space. Let's go further and explain more visually what's happening with another instructions. Second, other or fourth instruction in row was fill fragment. So if we have fragment reserved inside of the register file as a memory space, we have these instructions which enables us to fill with zeros those elements of the fragment C. So we putting 16 times 16 zeros with this instruction inside of the memory. So that's the purpose of this one. But we want to make it more visual and fully understandable, how to, in great manner and most reasonable manner, operate with the Tensor Core, because it's very important topic today. And so we describe this instruction. Then uh, fragment C must be neutral for the heading in start. So, but here for the matrix A and for the matrix B, and we said that they are responding to the sizes are responding to the fragment A possibilities, how many elements we can store in fragment A to be done on a tensor core. We are moving from the GPU DRAM, we are moving data from this matrix A, or from this location, or where this pointer is pointing, to the space on register file where, let's say, this pointer is pointing, and we are picking row by row, because we describe it or explain it to the compiler how to put data into memory. We're picking up row by row, and in each row 16 elements. In previous case, we defined how we're storing data when we reserve space. Also, similar we are doing with matrix B, which is same size as fragment B for this purpose. And for this case, we are from the location where B pointer is pointing out. From that location, we picking up as a defined column by column matrix of the 16 elements. Not matrix, column by column, and each column has 16 elements, and we do it column by column, all 16 elements per, and then 16 elements, and put it in a fragment B, which is inside the register file. And once again, these sizes are corresponding to each other. So we have these instructions now explained. Let's go further. Calling one kernel. Yeah, this is in global what's happening. Also, beside the thread and instructions which is executed on the tensor core, we have also forming, like, calling kernel with one block with 32 threads is for dealing matrix multiplication 16 times 16 matrices. So in tensor cores, yes, and this is the calling in the main program. We picked up that part which is not written down in previous case. This is repeated all operations. We moving A from the GPU memory to the frag A with this one. Load matrix sync, and also with this one load matrix sync, but for the B. Then put a fragment A, fragment B in a tensor core for the matrix multiplication operation, which should be one tact. And that's when we call one block with 32 threads. This is enough to done to this operation of the matrix multiplication and adding to be done inside tensor core. And that's how we're doing that with this instruction, which is MMA matrix multiply and add sync fragment A, fragment B, and pick up form C and store everything in fragment C. And then after we done operation and store it in a register file memory, we moving it to the top. So this part is calling, and this is how it calling to one operation 16 on the matrix is 16 by 16 to be done in one tensor core, and it must be done with the 32 cores. This is from the main program, unlike the previous stuff that we explained, which is actually like, yes, in previous cases explained by the as a kernel function. So when we call kernel function, it's dependent on the form of calling of that kernel function and how many threads is need to be used to do this operation. So they say it's 32 threads necessary inside of, or one warp is enough to execute this, or one block is need to execute this 32 threads to be formed to execute this function. Yeah, it's a little bit complicated, but I hope it's now more clear. And then after we done all these operations, we are from the register file, we moving that data for the other purposes into the GPU DRAM, which is also with this instruction load matrix sync from fragment B. Sorry, just to check something. I want to see one thing. Yes, no, it's not this example, but this one. You can see store. Yes, this is what I wanted to point out. You go from the in this case, when you're moving from the A to the fragment T, it's set up like this. But when you're moving from the fragment C to the C, it's set up like this. So let me check. Did we do it properly from the B? Oh, sorry, I didn't. This is wrong. So it's good that I made mistake, because that mistakes help you understand this better and properly. Yeah, this is okay. Let's. It's similar like host to device memory movement, or because you in one case you are moving data from one direction to another, and in this case, okay, store matrix sync. Yeah, this is storing operation. Previous operations were load, and here we have storing operation. And okay, we moving storing from the fragment C, which is given here. We are storing the data to the GPU memory, DRAM memory. So from the fragment C, 16 by 16 in this format, you are going row by row, and you picking up 16 elements. You're storing that in the matrix C. So sorry for this mistake. Once again, we are from the fragment C. Sorry. From the fragment C, we are moving data to the, or storing data with this operation to the matrix C, and then we are doing 16 by 16 elements row by row. So this mistake was cleared, so let's go further. Actually, there is no further. We have now useful data that we done, or which we have from operations in the Tensor core. So we can use that data further and go with that data in the CPU, and then we can represent the data on the screen if there is some need to. So this is last operation, last instruction in the set. This is also, yeah, this one is right, moving data from the fragment C to the matrix C, but this one wasn't good, but we changed it. And this is last operation in this section. So once again, we are moving from A to the fragment A, and we in this case, and these operations were load matrix sync, and this is store matrix sync. So when we store data into the GPU memory, DRAM memory, and this is loading of the register file memory. So to know difference. And the important thing is to know these differences between these instructions very well. This is for the reserving space. This is with the filling that space inside, also all other things inside the register file. This is from the moving from or loading from the GPU memory to the register file, also from the GPU to the register file. We've done the operation on the Tensor Core, and then we are moving that result data or store result data from the fragment C into the regular memory where data can be used, which is C, or C in GPU memory, and this is how we're storing it. This is form how we storing it, and so on. And I hope that we now better understand what we said practically in executing the program. The purpose of this video is to be more visual what we are doing and understand these processes very well, and so we can use these instructions further in purpose of doing stuff on Tensor Cores. So that's it for this time. I hope that I wasn't so much boring. Until next boring video from me, stay tuned and follow, like, share, and subscribe, blah blah blah, and try to learn. And if there is something which is not quite understandable, please let me know in the comments.